So in this video, I'm going to talk about a problem in the Fogler textbook that details an incident at the Monsanto plant. So this problem is taken from an example problem in chapter 13 of Fogler. So let me read the problem statement. So it says, a serious accident occurred at the Monsanto plant in Sauget, Illinois on August 8th, 1969 at 12:18 a.m. The blast was heard as far as 10 miles away in Belleville, Illinois. The explosion occurred in a batch reactor that was used to produce nitroaniline, which we'll call species A, from ammonia, which we'll call species B, and O-nitrochlorobenzene, which we'll call species C. In the reaction, A plus 2B goes to C plus D, where D is ammonium chloride. The reaction was carried out in water solvent. We'll denote water solvent as W. This reaction was normally carried out isothermally at 175 degrees Celsius and about 500 psi. A heat exchanger carrying water at 25 degrees C was used to maintain isothermal operation. The temperature was controlled by varying the flow rate of water through the heat exchanger. At slower flow rates, so when the water flows more slowly through the heat exchanger, the water would get warmer as it flowed through. This would make the heating less effective, but this was useful when not a lot of heating was needed to maintain the reactor temperature at 175 degrees Celsius. At higher flow rates, the water temperature remained constant, so you can flow the water really quickly through, and in doing that, the water doesn't change temperature as it flows through, and in doing this, you're maintaining the maximum cooling rate. Maximum cooling, hence, occurs at these higher flow rates. So the isothermal operation, so this reactor was intended to operate isothermally. The isothermal reaction, or the isothermal operation, was in part a safety feature of the reactor. This is because the reaction is pretty exothermic, with a heat of reaction of negative 590 kilocalories per mole. Further, it has a pretty low activation energy of just 11.2 kilocalories per mole. This means that the rate increases significantly with temperature, and the reaction gives off a lot of heat. So the reaction is giving off a lot of heat simultaneously. The rate constant increases rapidly with temperature. What this means is that as the reaction is proceeding and giving off heat, it can increase the temperature, which can increase the rate, and this can lead to significant increases in the heat. Maintaining an isothermal operation prevents this from happening. Further, at 300 degrees C, nitroaniline decomposes into non-condensable gases such as carbon monoxide, nitrogen, and nitrogen dioxide. Production of non-condensable gases leads to high pressure buildup and hence must be avoided. So this is another reason to maintain isothermal operation at 175 degrees C is to avoid getting anywhere near this 300 degrees C. The main safety feature on the Monsanto reactor was a rupture disk, which was designed to burst when the pressure in the reactor exceeded 700 psi. Rupture of the disk would decrease the pressure in the reactor, which would cause the water in the reactor to vaporize. This would remove some of the heat generated by the reaction through vaporization of the waters. The water absorbs that heat that's being generated and changes phase. Further, as the disk ruptures, steam is removed, so the pressure causes the steam to be removed from the reactor. Removal of the steam through the relief valve would remove significant heat from the reactor, with Fogler estimating that this would be around 45,000 kilocalories per minute. This should prevent, reaction one-way explosion, etc. So this works. So maybe because of this nice rupture disk and relief valve system, or maybe for another reason, the reactor was not equipped with a backup cooling system. Instead, when the heat exchanger would fail, an operator would run out and get it running again. And as long as the operator did this, within 10 minutes of heat exchanger failure, there hadn't been any problems to date. Now, the day the reactor exploded, several things had gone wrong, and this is a common theme in reactor disasters, is that it's never just one thing. It's usually multiple things going wrong at once. But on the day the reactor exploded, the reactor had been overcharged. So the reactor was designed for a charge of 3.17 kilomoles of A and 43 kilomoles of B, along with 103.7 kilomoles of water. However, the day the reactor exploded, it had been charged with 9.044 kilomoles of A, 33 kilomoles of B, and 3.7 kilomoles of water. It's speculated that Monsanto was interested in increasing production, so they increased the charge to the reactor. Also, the day the reactor exploded, the heat exchanger failed. So this happened sometimes, and one of the times it happened was on this day. And the technician was able to get it working, but it took the technician 10 minutes to get it working. And this is kind of on the upper limit of what the time at which the heat exchanger would need to be turned back on in order to avoid any sort of problems. So also on that day, the rupture disk failed. So because of that, this reactor exploded. And if you want to see a picture of that, it's in the Fogler book in chapter 13. So we are going to model this reactor to show that had any one of these things not gone wrong, the reactor wouldn't have exploded. And I don't mean to do that to say that reactor safety basically depends on having, these 3 requirements and that none of them ever go wrong. In reality, a reactor safety means having multiple layers of safety systems. So in reality, there should have been a backup heat exchanger. In reality, there should have been multiple rupture disks. Probably the rupture disks should function differently. So some, function from one phenomena, others function from another phenomena, and that way, if one type of phenomena can't operate for some reason, the backup ones will come into play. So those proper safety design would incorporate those things. This particular reactor was designed in a way that as long as everything went right, it wouldn't explode. We're going to model and show that. So we're going to show that. So first we're going to model normal reactor operation. And then we'll model the overcharge. When we do this, we're going to model the isothermal operation. We're going to model the failure, and then we're going to see how we change different parameters and what would need to happen, or how we could set these parameters to ensure that a safety incident would never happen. Okay, so here's some data about this, or here's some data about the reaction. We're given a rate law, a rate constant, activation energy. We're given system volume. So recall that the system volume is the volume of fluid and not actually the reactor volume. So there's 2 different system volumes that we're going to use, one for the design for charge and the other for the overcharge. We're given the heat of reaction, the heat of capacities of the species. We're given the UA term, the heat transfer term, and we're given the maximum, or the ambient temperature for the maximum cooling rate. So here's what we want to do. We want to determine an expression for the maximum cooling rate, QR max for this reactor. Then we're going to develop the mole balance for isothermal operation, and we're going to use it to determine the conversion and the heat generated after 45 minutes of operation, which is when the heat exchanger failed. We're going to do this in this video, we're going to do this for the intended charge. Later in class, we'll do this for the overcharge. And then we can compare that value with the maximum value of QR. What we want is for QG to be below the maximum value of QR. If the maximum value of QR is below that of QG, then runaway action is going to occur because we have we can apply the maximum cooling rate, but still not quench the heat being given off from the reaction. So what we want is for QR to be greater, or QR max to be greater than QG. Okay, so after that, we can model adiabatic operation for 10 minutes, and then we can determine what the values of conversion, temperature, and heat generated are. And again, at that point, we want the scenario where QR max is greater than QG. All right, so let's do this. For the first one, we're going to develop an expression for QR max. So let me get a pen here. Okay, so Q, and that's a little bit too thick. We'll take this pen, see how this works. Okay, there we go. Oh, except I don't want to type. Okay, hold on. All right. Maybe if we just take this. Third time's a charm, right? Okay, so QR max. This is going to be this heat transfer coefficient times the temperature in the reactor, T minus TA. TA in the maximum case, or the maximum cooling case, TA is going to equal 25 degrees C, or 298 Kelvin. So this expression also here is for the maximum cooling rate. If we wanted to look at the more realistic rate, or the rate that's occurring in the reactor intended to maintain isothermal operation, we would have the cooling fluid, which is water, would be changing temperature. We'd have to use a log mean temperature difference. We're not going to do this here because we're interested in the maximum cooling rates. The maximum cooling rate, we're able to flow that water through the heat exchanger very quickly, and what happens there is that it stays at 25 degrees C and gives you this maximum value of T minus TA. Okay, so let's see what our next question is going to be. Develop the mole balance for isothermal operation and use it to determine the conversion and heat generated after 45 minutes of operation. Okay, so we'll say this is problem 1 here. Problem 2, we're going to do the mole balance. So this is a batch reactor. This is a single reaction, so we're going to use a form in terms of x. So dx dt is going to be equal to minus Ra. Species A here is our limiting reactant, divided by Ca naught. So now we need expressions for Ra and Ca naught. Ra is going to be equal to the rate constant times Ca times Cb. That information was given to us. We have a value for the rate constant at 188 degrees C, and we can use the Arrhenius equation to convert that to the rate constant at whatever temperature we're interested in. So let's see here. We can say K is equal to K, let's call it K1 times the exponential of the activation energy, which we have, divided by R times 1 over T1. This value is going to be 461 Kelvin minus 1 over T. In the isothermal case, this is going to be, temperature is going to be this 175 degrees Celsius. I'm not going to try and add in my head quickly what that is in Kelvin, but that's the number that would go there. All right, so now we need expressions for Ca and Cb. Ca for liquid phase reaction is a simple equation. Cb is going to be Ca naught times theta B minus 2x because of the reaction stoichiometry. Theta B is going to be NBO divided by NaO. So we're given those values for both the reactor charge and the overcharge. Let's see here. And then I believe the only other thing we need for this equation is an expression for Ca naught. Ca naught is going to be Na naught divided by V. V is going to be equal to this 3.26 meters cubed for the design charge and 5.12 meters cubed for the overcharge. So we can go ahead and solve that. I believe we have everything that we need for that. And I've done that, and so I'm going to go grab those values. And let's see here. I find that, or I get a value of x. Let's see here. Okay, I get a value of x is equal to 0.068. Let's see what other information that we needed. This is after 45 minutes. Okay, so then QG is going to be equal to our reaction rate, RA, times our volume, times our heat of reaction. So RA we can get from our solution. That's going to be, if we insert all of our numbers into here, the value that I get for RA is negative 0.0014. And man, I would have to go back and see what the units are on that. Let's see here. Okay. That's probably kilomoles per meter cubed. Okay, so that is going to be kilomole per meter cubed per minute. Our volume for our design for charge is 3.26 meters cubed. And then our heat of reaction is, if we go back here, it's negative 590 kilocalories per mole, which is equal to negative 5.9 times 10 to the 5th kilocalories per kilomole. So let's put that, I'm going to put that on the next line. And the value I get for that is 2,710 kilocalories per minute. So that's a lot of heat being given off right there. In part probably because the volume is large, and also the heat of reaction is large. So even though the rate is kind of slow, we're still giving off a lot of heat. Okay, so then what would QR max be? So QR max is equal to UA, which is 35.85. And I would have to go back and grab the units on that. Kilocalorie per minute times Kelvin. Times the temperature. This is all in Kelvin. And so the value that I get for that is QR max equals 5,378 kilocalories per minute. So QR max is greater than QG in this scenario. What that means is that this is a good thing. So, the heat exchanger can control the heat. At this time, we'll say at this time in this scenario. Oops. Okay, so that's a good thing. Okay, so now let's consider the case where we have adiabatic operation. So now with adiabatic operation, we're going to need to involve an energy balance here. So we're going to take adiabatic operation for 10 minutes. And what we're going to do is we're going to start at this conversion here that we've developed. So the adiabatic case, we need to use an energy balance. And since it's adiabatic, we don't need to write the differential form of the energy balance. We can just use the algebraic form, since the temperature is only a function of the conversion. So that equation is going to be T is equal to T naught plus the negative heat of reaction times X. divided by the sum of theta I CPI. So in this equation, our T naught is going to be the temperature that the reactor is at initially, which in our case is 175 degrees C. So this is going to be 175 plus 273 in Kelvin. The heat of reaction, so let me move this down maybe a little. So I can write up here. The heat of reaction is negative 590 kilocalories per mole. So negative heat of reaction is 590 kilocalories per mole. That's important if you have an exothermic reaction, then it's going to be increasing the temperature, so you want this term to be positive. We have values for our theta I, so theta A is going to be equal to 1, theta B is going to be equal to NBO divided by NAO. So in our case where the reactor is at the design charge, actually I'm going to get to that in just a second. We're going to fill these in just a second. We're going to need the heat capacity here for, I have theta C, but really it should be theta water. Okay, and we know all the heat capacities. Those are all given in the problem statement up here. All right, so I'm going to make a couple of modifications to this equation. And that's because when I integrate it, I'm not going to integrate it starting from 0. I'm going to integrate it starting from the conversion that we ended at, which was this 0.68 here. So I'm going to modify this equation here. I'm going to take away that x, and instead I'm going to do x minus 0.068. That's going to allow my temperature to increase as a function of conversion at the start of adiabatic operation. So at x equals 0, we're in isothermal operation. So we don't want the temperature to start increasing at that point. We want it to start increasing once adiabatic operation is started. Okay, so then additionally for my theta terms, what I'm going to do there is take the final values of CACB that I integrated in my isothermal operation case, and then I'm going to use those to create theta B and theta C for the new case. So at the end of isothermal operation, I had achieved a conversion of 0.068. This results in a concentration of B of 6.18 kilomoles per meter cubed, and a concentration of A of 1.63 kilomoles per meter cubed. So that's my theta B for the beginning of adiabatic operation. So let me make a note here. We'll say these values are from the end, so T equals 45 minutes of isothermal operation, and hence they are the initial values of adiabatic operation. So similarly, it's going to be theta water. Of course, the amount of water never changed. That's going to be this 103.7 kilomoles. So 1 kilomoles divided by 3.26 meters cubed. That's the concentration of water over throughout, so the number of moles of water are not changing. And then we can take this so that's how I'm going to get all of those expressions. Now I'm going to switch over to polymath to show you how I do this integration. So now I'm going to show you how I used the free online polymath solver to solve both the isothermal and adiabatic operation cases. So the free online server only allows you to have 10 explicit equations. So that's what these equations are here. Because of that, I'm combining equations. Normally, if I wasn't limited, I would write everything out symbolically and define variables. That allows me better to check my work. Here I can't really do that because I need to conserve. You also see that I have multiple cases that are commented out. That's because I want to use the same code here to run the multiple cases. So I'm going to comment in and out as I go. Okay, so starting out, I have my rate law here. Then I have my concentration equations. You'll notice here I have instead of just x, I have x minus 0. I'll tell you why I have that in just a moment. I have my theta b here. Later I'm going to pull in a theta w. I don't need that right now. Ca naught. And my expression for my Q generated. Now I have my mole balance here and my initial condition. So this should give me the conversion and heat generated after 45 minutes of isothermal operation. So I'm going to click solve. And apparently I may need to relog it back in, so I'm going to. All right. Okay, so this is where I get my values. So my final value of x is a 0.68. This, I can get my final value of my rate. That's this 0.0014, and my heat generated term. This is also where I got my final values of concentration, which I'm now going to use in the adiabatic case. So now I'm going to take this code and write and modify it for the adiabatic case. So my rate law stays the same. My concentration equations, I need to add in this conversion term. So my initial concentration is going to be slightly reduced because I've already reacted some away under isothermal conditions. By adding the final, by subtracting out the final conversion under isothermal conditions here, that allows me to start at the concentration that would be in the reactor at the beginning of adiabatic conditions. All right, so then I'm going to take my theta b and my theta b, I'm going to take that based on the conditions or the concentrations that are in the reactor at the beginning. Those are these values here that I copied off of the output down here. All right, that gives me my theta b. Now I need also this theta water. I'm going to take my theta water term, and I need that because that's going to go in my energy balance expression. Okay, my Arrhenius equation stays the same. I'm going to comment out my isothermal temperature and instead include my energy balance. Here, again, I'm going to include this value of 0.068. I'm going to subtract that out. That's because the temperature doesn't start increasing when the conversion is at 0, because from 0 to 0.068, it's isothermal operation. So it only starts increasing after 45 minutes or after the conversion's reached 0.068. So I'm going to subtract that term out there. And then everything else should be all right. I'm going to come down here now to my initial conditions. I'm going to start at x equals 0.068 rather than 0. For time, I can integrate between 45 and 55. That would be fine. I can also integrate between 0 and 10. It doesn't matter. Both of those should give the same answer. All right, so now let's solve this scenario. Okay, so these are the values that I now get for this this case, under the design charge, after 10 minutes of adiabatic operation, I get a slight increase in my conversion to 0.086. I get a slight increase in my temperature from 448 to 462 Kelvin. And I can calculate my rate. That's this negative 0.002 kilomoles per meter cubed per minute. And then I can also calculate my heat generated term. So this is my heat generated for under this scenario is going to be 3,856 kilocalories per minute. If we go back and compare that with the maximum heat removal term, so that's going to be the 35.85 kilocalories per minute per Kelvin times reactor temperature minus 298 Kelvin, and I use a reactor temperature of 462 Kelvin, I get a maximum rate of heat removal of 5,879 kilocalories per minute. So that's the heat removal, or the maximum heat removal, is significantly greater than heat generated. That means under this scenario, the heat exchanger should be able to take care of the reactor contents. So even though the heat exchanger failed for 10 minutes, get it running again, the conversion still hasn't increased enough such that the temperature is so hot that the heat exchanger can't control the reaction, and the reaction can be quenched back to, either quenched completely or maybe even taken back to the desired temperature of 175 degrees C. So that's all I'm going to do here. In class, we're going to play with different scenarios to try to identify the set of operation parameters that could lead to reaction runaway and explosion. So we want to be able to avoid those. So can we develop a set of parameters and say we never want the reactor to get anywhere near these operating conditions? And we'll do that in class.